All right, so guys, this is where we are right now. We talked about this idea of equilibria being processes where the forward and reverse processes are happening at the same rate. Guys, we talked about an important idea, which was the idea that at equilibrium, the rates are equal. But guys, remember, at equilibrium, the concentrations are not equal, but they are... All right, they're constant. And guys, we related that to this wonderful little demonstration where we talked about the idea that, guys, and this is a great thing to come back to, the idea that the amounts of liquid in the tubes are analogous with concentration. The cylinders are analogous with concentration. These are analogous with K values, and then the rate is analogous to the amount of water which is moving in these tubes, which then gave us the idea that concentration times K, which is a rate law, gives us the rate of the reaction. Is that all coming back to you? Okay, so anything there you want to play with as you've had a chance to sort of stew over this for the last couple days? You guys okay? All right. So, guys, with that said then, this is where we're headed with this. So, guys, based on this idea of what you understand about equilibria, there are some conceptual things that you need to understand. Then we're going to start talking about representing these mathematically. That will bring us to Kc values, products divided by reactants. Then we're going to talk about the information that's contained within Kc values. Then we're going to write some Kc values, and then we're going to talk about Q values, which are different than Kc values, but they allow us to make predictions. So again, some general observations. Then we're going to talk about representing them mathematically. Then we're going to talk about this thing called Q, which allows us to take Kc and make predictions. So guys, I would encourage you to take notes. There are definitely some things along the way that are going to be important for you to have that experience of solidifying. But guys, right now I think we can say this, not writing it down, because we understand this, right? So guys, when we talk about equilibrium, we've got to understand the difference between what happens with rate and what happens with concentration. So let's be really sure we're sure. What happens to rate at equilibrium? Forward and reverse. What happens to rate? It's the same. What happens to concentration at equilibrium? And guys, that's represented in these two graphs. So allow these to soak in for a second, and then let's make sure that we're clear about how this all fits together. You okay with the ideas? So let me grab my writing utensils here, guys. Just a second, sorry. All right, so the idea here is that when we look at systems that come to equilibrium, we can look at this in two different ways. Of course, we're always talking about time, but if we're talking about time versus concentration, we know that we've reached equilibrium when the concentrations become constant. Now, guys, we've got A and B. Which one of these is the reactant? A and B. Which one's the reactant? How do you know it's A? Because you start with some. So guys, the idea is we start with no B, we start with lots of A. That makes A the reactant, that makes B the product. When we reach equilibrium, then those concentrations become equal. Notice, guys, what happens though to rate at equilibrium. When we're looking at rate over time, yeah, the rates do become constant, but importantly, they also become equal, and these are both identifiers of equilibria. Anything, is that all kind of review? You're kind of okay with that? Okay. So, guys, moving along from there then, this is where we need to start getting into some interesting ideas. Interesting idea number one is this, and you actually need to write down this reaction. So, guys, don't write down the pictures, actually write down what these are. This is the only named reaction that you need to know in AP chemistry. This is what is called the Haber process. And, guys, the Haber process is diatomic nitrogen reacting with diatomic hydrogen to form ammonia. It's a synthesis reaction. I don't know why they picked this as the only reaction you need to know the name of, but in the past they have said the Haber process, and they just expect you to know that it's nitrogen and hydrogen making ammonia, NH3. And you could balance it just by knowing both nitrogen and hydrogen are diatomic, but it's called the Haber process. That's not the point. Guys, this is the point, and this is something important that you need to understand about systems at Equilibria. Guys, this is some data that they gathered by studying the Haber process. Here's the question. Well, questions, and let me zoom into this for you. So guys, the question is this: how are these two trials different? And what does that tell us about equilibrium systems? Oh, and by the way, guys, this should be a double-headed arrow. This reaches equilibrium. So guys, how are these trials different? And what does that tell us about systems at equilibrium? Give you a second to think about it, and then we can talk about it. How are they different, and what does that tell us about equilibria? So guys, chat with the person closest to you. How are they different? How are these two trials different? Give you another second, and then we'll pull this together. And then we'll actually demonstrate it. So, guys, in order to answer the question, we might find that it's helpful to do this. So, let me catch back up. So, guys, how is trial, we'll call it left and right. Guys, how is the left-hand trial different from the right-hand trial? Where does the left-hand trial start? Lots of reactants. How much product? None. What about trial number 2? Lots of products, no reactants. But guys, if we could take these two graphs and superimpose them one on top of the other, what would we see beyond the point at which these reach equilibrium? They're exactly the same. Guys, this is an important point. When we talk about reactants and products in equilibrium systems, those names almost become meaningless. Because, guys, we've been trained to call the stuff on the left reactants and the stuff on the right products. But, guys, we also understand that there's a reverse reaction. And in the reverse reaction, the products become the reactants for the reverse process. And so the big idea is this: equilibrium systems will always settle down to the same ratio of left and right regardless of where we start. And guys, to drive that idea home, and again, I've told you, guys, this analogy only gets better as we play with it more. So guys, if you remember, was it 70-30? Was that the ratio? And it was like this, right? It was 70 product, 30 reactant. And so we started with 100 milliliters of reactant, and when we did this, we ended up with a 70-30 ratio. Well, guys, what about this? What if we start with all product and no reactant? What's this going to do? Well, here we go. Let's try it. So guys, as this reaction starts, we still have a small K value for the reverse reaction. We still have a larger K value for the forward reaction. But now we have no forward rate because we don't have any reactant. We have a large reverse rate because we've got a lot of product. And then just like before, we start switching these back and forth. What's happening to the reverse reactions rate? Reverse reaction. Speeding up or slowing down? Slowing down. Forward reaction, speeding up, because now we have some reactant to turn back into product. But guys, maybe now that you're seeing these move, what's going to end up happening? Where are we going to end up? 70-30. And guys, that's the magic of Equilibria. And that's what's represented on the screen up behind me. Because it does not matter where you start. You could start with all reactant, no product, all product, no reactant, a little bit of both. It absolutely does not matter. We will always end up back at that 70-30 ratio. Now guys, what if we did this? And I think you probably know this even from last year, and by the way, we're back to that ratio. Because what would happen if I just poured some of this off? And now if I allowed this to continue, will that end up at the 70-30 ratio? Well, kind of. It can't, right? Because we don't have a total of 100. But do you understand that it will end up at 7-3, even if it's not 70-30? And guys, the idea is that product-reactant ratio, which we've already talked about last year, but we're going to dig into more, is called the equilibrium constant. And it really is a constant. It doesn't matter how you get there. It doesn't matter how much stuff you start with. You'll always come back to that same ratio, which for our little dude is 70-30. But guys, for all of these reactions, they have Kc values. And you can actually look them up in here. There's actually, you could look up the Kc value for the Haber process in here, and it really is a constant because it doesn't matter how you get there, you're always going to end up at the same equilibrium. You guys good on that idea? Okay, so with that said, you now know that we need to know the Haber process. Any questions about this idea of it doesn't matter what direction we come at it from? Is that okay? All right. So then, guys, we're going to move forward, and we're going to talk about, and we did this last year, but let's do it again. Let's make this mathematical. And guys, I would encourage you not to necessarily write down the words, but I would encourage you to write down the equation if you don't remember. So guys, we can take this idea of equilibria and we can describe these ratios mathematically. And when we do, it's a ratio of products over reactants. And so guys, I would encourage you to write this down. So you've got W moles of A, X moles of B. That's in equilibrium with Y moles of C and Z moles of D. Now guys, based upon what you learned last year, do you remember how to write the Kc values? Do you remember? Let's review. So what happens to the coefficients? They become exponents, and then we don't add in our equilibria, we multiply in our equilibria. So is it a surprise then that that would be the Kc value for this? Is that okay? So guys, I don't know if we talked about this last year, but do you know what the C stands for? No, we should talk. So guys, what do the brackets mean? Concentration, molarity, and that's what the C means. So guys, when we write Kc values, literally that C is the subscript C indicates that this is a concentration or molarity ratio. Now guys, that's important to keep track of. Let's see if I can do this in my head. That's important to keep track of because in a minute we're going to do Kp. Then generically in chapter 16, we're going to talk about KEQ, KW, KA, KB, KSP. Shoot, there's one other K value we're going to talk about. There's like 8 of them. So what do all these K values have in common? Guys, K values are always equilibrium expressions, and K values always have products over reactants. That's the commonality. The different things like Ka, Kb, Keq, Kw, all of those things depend on the system that we're studying. But guys, K is always at equilibrium, and it's always products divided by reactants. Now, this is not critical, but we should say this, because when we talk about these Kc values, understand that we can write Kc values directly from the balanced equations, because in Kc values, the coefficients are the exponents, because these are only reliant on stoichiometry and not on mechanism. Because guys, you know you can't write rate laws from balanced equations, because in the background the mechanisms are complicated. But on the front end, when we talk about equilibrium expressions, these you can write from the balanced equations because it all just depends on the stoichiometry. It doesn't matter on how they get to equilibrium, it just matters where that equilibrium is. So, guys, I know some of this is review. Anything there you want to explore about Kc expressions? You okay? Okay, we're going to shift gears then. Guys, and I really think just you need to write down the not the words, but the expression. So, guys, in this chapter, we are also going to be introduced to the idea of gas equilibria. So you may just want to write down gas equilibria. So, guys, when we're studying gases, we can actually, especially gas systems that go to equilibrium, we can actually express gas. We can represent and study gas equilibria similar to the way that we look at molarity equilibria. The only difference is instead of talking about Kc, we're now talking about Kp. But then, guys, notice the difference. These are the pressures of the component gases. So no longer molarity, we're now just talking about partial pressures. So it's the pressure of gas C, it's the pressure of gas D, it's the pressure of gas A, the pressure of gas B. So fundamentally for you, the problem-solving process is the same, but instead of being given molarities, you'll be given pressures, and you'll just plug those in and solve as well. So those are the two equilibrium expressions that we're going to talk about in this chapter. And then when we get into 16, it just blows up, and we've got A's and W's and B's and SP's, and it just goes crazy. You guys doing okay? What a weird way to start the week. Were you guys' classes just empty first period? Yeah. And I totally forgot about this. So for the first time in my life, I had to send an email to all of my students using Skyward. It actually worked pretty good, I think.
You've ever done it before?
No, I mean, Miss Call and I, and maybe we're wrong, but we have this naive idea that we do a good enough job communicating in class that, frankly, and as a parent, I know that most of the emails that I get from my kids' teachers, I just delete. Does that make me a bad person? And so our belief is that we're usually well enough prepared and clear enough at communicating that sending home these emails isn't necessary, but it was yesterday because we realized we totally dropped the ball. So, what's that? Cole, could you explain this, please, to Josh?
I'm a little lost.
We forgot about college day.
Okay.
Yeah. We didn't. Well, because you guys didn't get to do it last year because of COVID.
Juniors college day?
Yeah, so this has been a thing for decades where they bring representatives from colleges, mostly Utah colleges, to campus, and it's Q&A sessions. Frankly, it's recruiting for them. But last year, we even did it in 2020 because we got it in not knowing, it's usually in January. COVID blew up in March. Last year, we didn't do it because we couldn't. So you guys are like the first group, frankly, probably since I've been teaching, that didn't do a college day. So, which is weird. I wonder why they didn't invite you to this year's. I guess at this point you've already picked your schools.
Yeah.
So, yeah. Yeah. At some level it would be a waste of time. I hadn't really thought about that. That's interesting. I don't know. Anyway, so you guys got on this idea of KP? Is that all right? Okay. So, guys, this then, and I want to make sure you hear this, because this was a mathematical part of the AP curriculum. It's no longer a part of the curriculum, but I fear I may have left the question in the homework, and it's this. Guys, it turns out that if you have a system at equilibrium, you can actually figure out the Kc for that system and the Kp for that same system. It's a little bit sneaky, but it turns out that what you can do is this. Well, so imagine that we have a system that's in a 1-liter vessel, and we've got gas A, we've got gas B, we've got gas C, and we've got gas D. What we can do is we can figure out the pressures of A, B, C, and D. We can plug the pressures into this expression, and we can figure out Kp. But the other thing that we can do is this. We can measure the number of moles of A and B and C and D. And then remember, molarity is moles divided by liters. And when we think of molarity, we're thinking moles per liter of solution. But with gases, you can actually cheat. And you can say moles of particles divided by the volume of the container in liters. And that allows us to kind of do Kc calculations with gas systems. And so the idea is that if you knew the pressures and you came up with Kp, and then you knew the number of moles, and you knew the volume, and you calculated molarities and plugged that into Kc, you could come up with a Kp and a Kc value for a gas system. And it turns out they're generally not the same. There is a relationship, though, and it used to be on the AP equation sheet, and it's not anymore. So, guys, when you get to that question, I think I forgot to pull it out of the homework. Guys, when you get to the question in the homework, you might want to read over it, but you're not going to see it in the AP test simply because it's not a part of the curriculum anymore. Okay, so guys, big deep breath. Equilibrium, come at it from any direction. These things are constants. We talked about Kc, which is the concentration ratio, products to reactants, and Kp, which are the pressure ratios, products to reactants. Anything there you need to talk about? You guys okay? All right, so let's move forward then, and let's talk about what these K values are all about. See, guys, these K values are going to become wildly important to us in Chapter 16. So for now, this is sort of an end unto itself. Hey, what's the K value? Let's solve for it. That's going to feel big and important, especially when I see you on Wednesday. But then, guys, what you're going to find out is that in 16 and 17, these K values are going to become things that we're going to use conversationally to think about how systems behave. So guys, let's talk about the information that's contained within K values. As you're doing this, it's going to be important to remember that K is products divided by reactants. Fundamentally, K is products divided by reactants. So guys, with that in mind, we can then, I think, probably figure this out. So first of all, we can talk about the directions that reactions proceed as they get started. So guys, what does it mean if we have a reaction with a really big K value? If K is big, do we have more product or more reactant? More product. So guys, if we've got a K value, a Kc value that's large, this reaction favors products. It's going to make a lot of product. The numerator's bigger. And guys, understand, when we start looking at this in greater detail in the coming days, these K values, I mean, it's unbelievable their magnitudes. Like, we're going to look at K values on the order of 10 to the negative 15th. Like, really small. And 10 to the 8th, 10 to the 9th, really big. So these values have an amazing range. So if you've got a KC value, a K value that's big, you're going to have a lot of products. This means that the equilibrium lies to the right. And guys, we can talk about it in either way. We're going to talk about equilibrium to the right. We're going to talk about it as favoring products. Either is fine. And then, guys, obviously the converse is true as well. If you have an equilibrium where Kc is small, and guys, don't confuse small with negative. We'll talk in a minute. But if Kc is small, much less than 1, then that reaction favors reactants, and the equilibrium lies to the left. So scratch it into your notes. Let's talk about what this means. And then we're going to start writing some Kc values. You guys good? So let me offer to you a way to think about this. Guys, what I like to do when I interpret this idea of Kc big or Kc small, what I like to do is ask myself, which one is bigger? So if Kc is large, that means the numerator is large, and that means there's more product. If Kc is small, that means the denominator is large, and that then means that we're going to have more reactant at equilibrium. So rather than thinking big and small, I just like to think which one needs to be bigger to make this true. So big values, big numerator, big product. If we've got a small value, big denominator, big reactant. And that's the way I like to think about it. But guys, what about this? Imagine that if we have a Kc value that's on the order of like 10 to the negative 8th. Does that mean more reactant or more product? More reactant, because this is a very, very small value. But guys, remember, that does not mean negative. Why is it impossible to have negative Kc values? Can't have negative concentrations, right? You can't have less than none. So guys, Kc values are always positive, but they can also be very small. And I know you know this, but just to be sure, the idea is that negative exponents don't mean negative numbers. Negative exponents just mean less than 1. Less than 1, but bigger than 0. Does that sit okay? Okay. So guys, then this. Imagine if we wrote a Kc value for this, where we've got reactants on the left, products are on the right. We do the Kc value. That would be concentration of products divided by concentration of reactants and so on. But guys, again, we talked about the idea that reactant and product is kind of arbitrary because really the products are turning back into reactants. So guys, what if we did this? What if we just arbitrarily flip the reaction around and we put the products on the left and the reactants on the right? What would that do to the value of Kc? What would it do to this fraction? Flip it over. And guys, when we flip a fraction over, mathematically that functionally means it's 1 over Kc. So if we're flipping this over, we also flip Kc over. And so guys, you just need to know that if we switch the direction of the reaction, then Kc flips over as well. All right, so guys, we've got 2 more things to do, and we are done for the day. You guys okay? Yeah? No, it's funny because as I was writing this down, I realized we didn't talk about it, but I feared that talking about it would be distracting. But no, thank you for bringing us to it. So, guys, Maddie was pointing out, do you remember this? That Kc is a dimensionless number. It doesn't have units. And so it's not technically that the molarities all cancel out, because sometimes they don't, but we understand it to be a dimensionless number. It's not a measurement of something. It's a comparative ratio between things. And so it doesn't have units because we're not measuring something. We're comparing things that are functionally the same. So it's a dimensionless number. It doesn't have units. Okay. All right. You guys good? Are you caught up to here? So, guys, we've got two more things we need to talk about. The next thing we're going to do is we are going to look at what are called hetero and homogeneous equilibria. Guys, please don't miss this. This is one of the things that they're going to try to trip you up on the AP test. You're going to see, we're going to go over this, and when we get into chapter 16, you're going to be like, oh shoot, I did that wrong and I totally forgot. So guys, this is important. Then after that, we're going to go over something called reaction quotients, and then that's going to be our day. I know this has been sort of a potpourri of stuff, but guys, we're just we're pulling together all these things that we need to know about equilibria that we're going to be using for the next 2 months. So let's do this first. Types of equilibria. Guys, this is worth writing down. These are things that you really got to keep track of. So, when we talk about types of equilibria, you've probably noticed that there's a lot of things in this class in chemistry that can come down to homo and heterogeneous. We have homo and heterogeneous materials. We have homo and heterogeneous catalysts. Well, guys, we also have homo and heterogeneous equilibria. But the terms mean the same thing. So if something is homogeneous, all of the players in the equilibria are in the same phase. Hey. So guys, an example of this is the Haber process. Nitrogen is a gas, hydrogen is a gas, NH3, ammonia, actually is a gas. We dissolve it in water to turn it into a cleaner, but it's actually a gas as well. So if we have all the substances in the same phase, that's homogeneous. Then guys, obviously we have heterogeneous equilibria. And in this case, the substances are in different phases. So guys, I know I told you this a couple days ago, but we're going to continue to do this. Throughout the year, throughout the remainder of the year, we're going to increasingly be bringing you back to things that you've learned and maybe forgotten. One of those things I would propose to you are solubility rules. Shall we? Oh, yeah. So guys, do this with me. Let's go 1 molar Ki, 1 molar 1 molar Ki, 1 molar lead-2 nitrate. Do not write the net ionic equation. Oh boy, that's another thing you forgot. Guys, please write the complete molecular equation for the reaction that would happen between a 1 molar solution of Ki and a 1 molar solution of lead-2 nitrate. Now guys, listen. Before you start writing, listen. We've talked about this before, but we're going to talk about this again. Guys, when you sit down to the AP test, every single question that you read on the AP test, your first response is going to be, oh crap, I want out of here. Seriously. Like full-on fight or flight syndrome, y'all. Your hands are going to get clammy. Some of you will start fidgeting because that's your nervous response to stress. Guys, right now as you're reading this question, some of you are thinking to yourself, oh crap, I have no idea what to do. Welcome to the AP test. Guys, the most important thing that you can do is what you do next. Because right now, if you read this and you say to yourself, oh, that was 5 months ago, I don't remember how to do this, that's okay. Knappenberger's going to show me in a minute, and I'm just going to sit here and just wait for the answers to come to me. Guys, without knowing it, you are training yourself to quit when you don't know immediately what to do. That's what the AP test is going to feel like every single question. So guys, what you got to do right now is you need to start training yourself. You need to start building habits, building capacity that says, when I don't know what to do, what am I going to do? And guys, many times that is just start writing stuff down. So what is it that we're going to do? We're going to write the complete molecular equation. What do all chemical reactions have? A yields arrow. So guys, this could be a significant victory for you just by writing down the yields arrow. So write down the yields arrow. Now you're doing something other than nothing. And now, guys, maybe you find a next step. So now that you've got your yields arrow, you now know you've got reactants and you've got products, but you already know your reactants because they're on the board. So maybe you write those down, and you write them down in a way that feels kind of like a reaction. Now we're getting somewhere. And now maybe whether you can give it a name or not, you look at this, and let's not even give it a name. But guys, what are these two things going to do when they get together? Switch partners, right? So why don't you start switching some partners? You don't even need to know that that's a double displacement reaction. So guys, let's start switching some partners. Yeah. So guys, you will have, Kate's question is good. Guys, you will have our stripped down periodic table, and that's it. But understand, you will not have an ion chart. So this is where we start to review the charges of ions, because guys, even without a periodic table, you should know, and I'm going to switch colors, you should know that nitrate's -1. You should be able to look at a periodic table and know that everything in group 1, including potassium, is +1. You should know that everything in group 7, including iodide, is -1. But guys, lead, and you don't even need to know this, lead can have more than one charge. But in this particular instance, what does the charge of lead have to be? +2. Because this is -1 and there's 2 of them. So guys, by reasoning through that, which may have taken you 3 to 4 minutes and multiple moments where you're like, I just want to quit. At that point, you're just breathing deep and slowing down. Now guys, we can figure out how these rearrange. So what does the K hook up with? The NO3. And then guys, what about the lead? The iodide? But this isn't it, is it? Yeah, it's that. And then we need to balance it. So we've got 2 iodides, so we need a 2, and then we need a 2. Okay. You use parentheses when you have more than one of a polyatomic. So notice that this is not in parentheses because there's not more than one of them. Notice this is not in parentheses because it's not polyatomic. So the only time we use parentheses is when there's more than one of a polyatomic. Now guys, at this point it would be really easy for me to lie to you, but I'm not going to. We're just going to talk about this for real. What we're going to do, guys, is we are going to write the Kc value for this reaction. But understand, guys, that's actually nonsensical. It's stupid. Because this is actually not an equilibrium process. And we only write Kc values for equilibrium processes. But guys, you don't know enough chemistry right now for me to have put in front of you an equilibrium process that we could write the Kc value for. So guys, this is wrong, but we're going to do it anyway. We're going to pretend like this reaches equilibrium, even though it doesn't. So guys, what I'd like you to do, please, is now write the equilibrium expression, the Kc expression, for this reaction. You guys okay? So guys, this is important. This is the part that's going to bite you in the butt in the next unit. Check this out. So KNO3 squared PBI2 KI squared Yeah. Oh, wait. Yes? No. Guys, this is not the equilibrium expression for this reaction. But please don't get caught up in the reason you got this wrong. Get caught up in the bigger idea. So, guys, this is the deal. Looking at this reaction, we understand that this is a double displacement reaction. Don't let this be the important point, though, guys. See past this. So, guys, we understand that this is a double displacement reaction, but do any of you remember the solubility rules well enough to know that this is a special kind of double displacement reaction? It is a precipitation reaction. Guys, do this with me. Ki is aqueous. Please write this in with me. How do I know with certainty that Ki is aqueous? How do I know with certainty that it's got a molarity? So guys, what about the lead-2 nitrate? Also aqueous because both of them have molarities. Guys, again, as you're learning to solve, as you're learning to avoid panic, as you're learning to write things based upon limited information, that's a huge one. Things that have molarities dissolve in water. I know. But now, guys, this. In order to figure out the products, now we need to know solubility rules. And guys, again, these are things that you memorized, you made tables, you took a quiz, da-da-da-da-da-da. But if nothing else, you should remember that there's a magic little solubility rule for nitrate. All nitrates are soluble, which means that this is soluble. But guys, maybe you also remember the rule that says all halogen-containing salts, iodine, bromine, chlorine, fluorine, these guys, fluorine, chlorine, bromine, iodine, all halogen-containing salts are soluble unless they're bonded to silver, lead, and mercury. And guys, here's our lead, and specifically lead-2. This is a solid. Now, Guys, follow this reasoning. And if right now you're having this little come apart up inside your brain because you're like, oh crap, I don't remember the solubility rules. Guys, nobody remembers the solubility rules at this point. That's why we're going to start reviewing. That's not the point. Here's the point. Is this equilibria homo or heterogeneous? Heterogeneous. Aqueous, 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 solid. You can picture the lead 2 iodide at the bottom of the beaker. That's the way we draw it. We would draw it like this, and the PbI2, this is the convention on the AP, it's on the bottom of the beaker. But guys, listen carefully. Don't miss this. If this is the lead 2 iodide on the bottom of the beaker, what is the molarity of the lead 2 iodide? What is the molarity? So what phase is the lead 2 iodide in? It's a solid. How much of it's dissolved in water? None. It's a precipitate. It doesn't dissolve in water. So what is the molarity of the lead 2 iodide? It is 0. But guys, hold on. We don't, however, think of it as being 0. We think of it as if asking the question fundamentally makes no sense. And as a result, we write it out of the equilibrium expression. So guys, the deal is this. When you write equilibrium expressions, solids get excused from the equilibrium expression. Why? Because they don't have molarities. But guess what? Liquids get written out as well. Because liquids also don't have molarities. Sorry, guys. And realize that when we say liquids, we don't mean stuff dissolved in water. We mean liquids. Liquids do not show up in equilibria either because they don't have molarities. So guys, fundamentally, liquids and solids never show up in your Kc expressions because they don't have molarities. They also don't show up in Kp expressions because they don't have pressures. They're not gases. So guys, again, the idea is that solids and liquids never show up in equilibrium expressions because they don't have molarities and they don't have pressures. You guys sold on that? Solids, liquids, never in K expressions. Okay? So let's summarize that like, drawing dots. So the summary then is this. The idea is this, guys, when we're writing Kc expressions or Kp expressions, we do not include factors for solids or liquids. Now, guys, understand that the actual reason for why this is the case is actually a little more complicated than just saying they don't have pressures and they don't have molarities. We're going to leave it at that. We'll let your university professors give you the big picture, but the rule stands. And so we're going to leave it at that. You guys okay on that idea? With the understanding that when we get to chapter 16, most of you are going to forget we ever had this conversation, and you're going to screw them all up anyway. But we'll talk then. You guys okay on the idea? Can we do one more thing and call it a day? Okay. Guys, I love that this is how we get to wrap up the day, simply because we get to go back and do our little demonstration again. Here, hold on a second. Yeah, okay. So guys, these are what are called reaction quotients. This is good stuff. All right. Hold on. Let me think about how we're going to organize this. Okay, so do this with me. We're going to go reactant in equilibrium with product. Then, guys, we're going to write the Kc for this. concentration of product, concentration of reactant, and then we're going to make this specific to our little dealy thunker here. 2.3, is that the math of that? 7 divided by 3 is 2.3, is that true? Okay. So guys, do that with me. But now guys, this is an important point. You didn't even know to make this distinction, but in order for this to make sense, you've got to make this distinction. So guys, 70-30. Let me even build it. Reactants, products. Which one's products is bigger, right? Yeah. Being wildly sloppy with parallax. No, maybe I shouldn't. Ooh, that was way too much. Yeah. Yeah. All right. All right. So, guys, the idea is this. We know that when our little water tube system comes to equilibrium, our little water tube system settles down at 70-30, right? Oh! If you guys saw what I just saw, you would believe in God. That was unbelievable. I had this moment where I'm like, do I dive? What do I do? And I realized it was just out of my hands. Little disappointed because I know that someone in this room saw this thing rolling to the edge and you said nothing. Shame on you. But this thing rolled off horizontal, turned vertical, landing on the rubber thing, bounced, landed on the schnozzle, and then laid down. If it had done, well, no, okay, so maybe that's not divine, because this end's heavier, causing it to rotate. I'm still going with God. I'm choosing to believe.
Because that's glass, isn't it?
Oh, yeah.
It should have shattered.
That's my point. Whew. Oh, yeah, we saw it right there. Some of you are going, I hope that happens when I take the AP test too. It may. You don't know. Okay, so guys, 70-30, right? But guys, let's remind ourselves, what does the 70-30 represent? Concentration. But guys, concentration at what magical set of conditions? Well, here, at what magical set of conditions? When is this 70-30? At equilibrium, and it's at equilibrium because the amount of water in the tubes, which is representative of rate, is equal, yes? Okay, now guys, this. Let's now do this. Let's go this way first. I'm going to add some reactant. I'm going to bring this up. Oh. I'm going to bring this up to 70 because that's math that I can do. Remember, I went to public school. Okay, so now guys, that's 70. Would you write this down with me? Hold on, I got to think about... We'll write it over here. Well, hold on. So now, I'm going to write it over here. So guys, now looking at our Kc value, it's still products divided by reactants, so I don't need to do that there. But now guys, we're down here. And this thing is 70 divided by 70. And again, that's math I can do. That's 1. But now guys, this. What are the 70 and the 70 representative of? Still molar, still concentration. But now we are no longer at the concentrations. Now we are no longer at the concentrations where this is at equilibrium. Still concentration, but not the equilibrium concentrations. This has a brand new name. Write this down with me. This is still products divided by reactants, but it's no longer called Kc. It's now called Q. So guys, please don't write this down. I'll give it to you in word form in a minute, but let's define it. What is Q? Q is Kc at non-equilibrium conditions. Let that sit in. What is Q? Q is Kc at non-equilibrium conditions. So guys, watch. Is this at equilibrium? No, how do you know? Because it's not 70-30. So this is not at equilibrium, we can't call it Kc because it's not the equilibrium concentration ratio. We now call it Q. Is that okay? Now this. Guys, which one is bigger in our demonstration now? Hey, which one is bigger in our demonstration now? Q or Kc? Which is bigger now? Kc or Q? Kc, so would you draw a big old alligator eats the bigger number? So guys, and if you want to write this out, you can, because this is the important bit. Kc is now bigger than Q. Kc is now bigger than Q. Here's the question. When I now do the to-be flippy thing, guys, which one's going to go up? The products or the reactants? Products. So as we now do the to-be flippy thing, reactants are going down, products are going up. This may run off the scale of the graduated cylinder for products. But guys, eventually what's going to happen? It's going to go back to equilibrium. Will that equilibrium be 70-30? No. But it will be what? 7-3 or 2.3 to 1, right? So guys, this will go back to equilibrium. It's just that it's going to be an equilibrium that's not exactly, it's the same ratio. And it's going to go back to 70-30. Now guys, here's the trick. As it did that, listen, as it did that, did the reaction go to the right or to the left? Did it make more product? Or did it make more reactant? It made more product. So guys, the idea is this. When Kc is bigger than Q, this reaction will shift to the right in order to return to equilibrium. When Kc is bigger than Q, the equilibrium will shift to the right, or we could say it will shift towards products. It will make more product in order to get back to equilibrium. Now guys, let's model the other example. I'm going to put this back at equilibrium. So reactants, I am struggling. Reactants are 30. Products are 70. So this is back to equilibrium. Now guys, let's do this. Let's pull out some product. No. Sorry. Let's go back to 70. Sorry. Okay, so there we are at 70. But now guys, let's go in the other direction. In this example, we added reactant. Now let's look at the other example, and let's add product. And let's take this up to 90. Hey, again, that's math I can do. Okay. So now, guys, recording the data, now we are at this set of conditions where products are 90 and products are 90, reactants are 30. So again, figuring out that value. Are we comfortable with the idea that this is Q because it's not at equilibrium? And this is 3. So now which is bigger, Q or KC? Q is bigger. So Q is bigger than KC. So if Q is bigger than KC, now what's the reaction going to do? Well, let's do it. So now, guys, as we do this reaction, 90-30, and even from a distance, you can see what it's doing. Products are going down, and reactants are going up. And again, when is this going to stop? When it gets back to that 2.3 to 1 ratio. But guys, as this is happening, which one's going up? Products or reactants? Reactants. So what that means is that this reaction is shifting to the left, or it's shifting to reactants. So guys, this is fundamentally what you've got to be able to do with this idea of Q values. Again, in review, Q is Kc solved at non-equilibrium conditions. So what do we use Q for? We use it as a predictor of the direction the reaction is going to go to get to equilibrium. You guys good on that? Because for me, that brings up a question. How on stinking earth am I supposed to remember this and this if I don't have tubes in front of me? And guys, here's what I like to do. Say, for example, Q is bigger than Kc. This is the thinking that I use. If Q is bigger than Kc, and if Q or Kc are both products divided by reactants, if Q is bigger than Kc, which one's too big, the top or the bottom? Let me say it again. If Q is bigger than Kc, which one's too big, the top or the bottom? The top. You've got too much product. So what do you need to do to get rid of product? Turn it into reactant, and this shifts to the left. Now guys, what about this? What if Q is too small? What if Q is smaller than Kc? Well, if Q is smaller than Kc, now which one of these is too big? The bottom. And in order to fix that, you got to turn bottom into top, and that shifts the equilibrium towards products. Guys, that's the way that I think about it. I think about which one's too big, and once I can identify the one that's too big, getting rid of it is the direction it'll go to get back to equilibrium. Does that make sense? Okay. So guys, write down what of this you believe you need to. So guys, first of all, this. Okay. So this. So we use this thing called Q to predict the directions of the reactions. To do this, we plug in what we call instantaneous concentrations, which are simply concentrations that are not at equilibrium. This is called Q. This tells us the direction the reaction will go. In chapter 20, it's going to be obvious but important to understand that when Kc and Q are the same, that's equilibrium. But then, guys, this... Oops, sorry. At any other set of conditions, then, guys, as we said, Q tells us direction. Are you guys writing this down, or are you okay? I'll give you another second. You guys okay? So this is not enough, but it's not bad. Guys, this is the way the book represents it. It's not bad. Understand that this is not really like products and reactants. It's simply a measure of relating Q to Kc. So the idea is this. Over here, KC is bigger than Q. So guys, if KC is bigger than Q, which is too big? If KC is bigger than Q, which is too big? The denominator. I don't even like to think I just think bottom. So guys, the idea is that Q is too small. And if Q is too small, the bottom's too small. And what's in the bottom? The reactants. So that means what we need to do is, in order to get to equilibrium, we need to form more products. So we got too much reactant. We're gonna form more products to get rid of the reactants. You see the connect? I don't know that I love this, but I like it better the way that we drew it. The way that we drew it here. But guys, at some point, in some way, you need to understand this relationship between Q and KC. You guys okay? All right. So guys, we're done. This. I think you already snapped that or wrote it down. Guys, that's what we're up to. We will look at this on Wednesday. We're going to do some fun math on Wednesday, but we're going to take a break. We'll come back. I think we're going to have, we'll talk. I think it's going to be a chill day in lab, and then we'll see where we're at.